This video is about inverse hyperbolic functions and their derivatives. As always, begin by reading through the textbook and taking some careful notes, but now consider the following highlights for this topic. We'll begin with the definition of the inverse hyperbolic functions in terms of logarithms, which will be provided on an assessment, so we don't have to worry about memorizing these. And the first is as follows. The sine hyperbolic inverse of x function is defined as the natural log of x plus the square root of x squared plus 1, where x squared plus 1 are all underneath that square root. Now, this is defined for x being any real number. Moving on, we have cosine hyperbolic inverse. And by the way, we've also discussed the shorthand way of saying these. So sine hyperbolic can be sometimes said as sinh, cosine hyperbolic cosh. And so if you use those, you can call these sinh inverse of x or cosh inverse of x. Anyway, cosine hyperbolic inverse of x is defined as the natural log of x plus the square root of x squared minus 1. You'll notice a subtle difference there, whereas the sine inverse or the sine hyperbolic inverse had an x squared plus 1 underneath the root. The cosine has the minus. So those details matter. Of course, we don't need to memorize these perfectly since they'll be provided, but it's just helpful again to recognize those keys when using each of these formulas. And this is defined, cosine hyperbolic inverse of x is defined where x is greater than or equal to 1. Moving on, thirdly then, the tangent hyperbolic inverse of x function is as follows. It's 1/2 times the natural log of a fraction whose numerator is x plus 1 and whose denominator is 1 minus x. Now, this is true for x being strictly between -1 and +1. That is, x is greater than -1, but less than +1. All right, so we'll be doing examples with these definitions shortly, but this is at least understanding what they are. Now, we can also discuss derivatives of these inverse hyperbolic functions, which again will be provided on assessment, so we don't have to memorize these. But as we go through these formulas, I want us to remember that, as always with derivatives, we need to use the chain rule as applicable. Now, as you'll recall, the chain rule applies when you have a composite function. And so the way these formulas are given here does not include them, but we're going to eventually use the chain rule, which I'll make more clear as we go. We have the derivative of the sine hyperbolic inverse function of x, which is defined as a fraction 1 over the square root of 1 plus x squared. The derivative of cosine hyperbolic inverse of x is equal to a fraction which is 1 over the square root of x squared minus 1. And again, these will be provided, so you don't have to worry so much about memorizing them, but we do have to know how to use them. We'll be practicing those in some examples shortly. Moving on, the tangent hyperbolic inverse derivative is 1 over 1 minus x squared. The derivative of cosecant hyperbolic inverse of x is equal to negative, there's a negative in front of it, be careful with that. It's a fraction which is now 1 over, the denominator is the absolute value of x times the square root of x squared plus 1. So a few pieces going on there. Moving on, the derivative of secant hyperbolic inverse of x is negative 1 over x times the square root of 1 minus x squared. And lastly, the derivative of cotangent hyperbolic inverse of x is 1 over 1 minus x squared. All right, so with those being the formulas that we're going to use, of course, we'll practice them shortly, and I'll even use the chain rule in some examples so you can see how that works. But these are the most basic of these derivative formulas. Let's try some examples now where our instructions say find the derivative of each function, simplify where possible. And our first function given is f of x equals sine hyperbolic inverse or sinh inverse of -2x. So with an input such as negative 2x, you'll notice the formulas we have defined above only had the simple x as the input. So this is where we have to be careful with the chain rule. In fact, some textbooks might even list the formula that we have above using the chain rule. For example, you might see something like the following, which I'll write here. So the derivative with respect to x, which I'll say is d over dx of, I'm going to put the general form here, so sine hyperbolic inverse of u. So I'm going to use u as some implied function of x. This is typically what might be done to include the chain rule in the definition. So the derivative with respect to x of sine hyperbolic inverse of u would be equal to, well, the formula that we already know for it. So if you look above, you're just using the same formula, which is a fraction which has 1 over the square root of 1 plus, now we said 1 plus x squared above, but that was the most simple form of it. If u is some other function of x, then you might see it written as 1 plus u squared, but then you'll also have to multiply by the derivative of u. So we'll say times u prime. And this is a way of just including the chain rule with the formula. Again, some textbooks put it this way. Some put it in the simple form that we have above, but ultimately we have to accomplish or use this chain rule where applicable, and this is an example of it. So what we're going to do is say, for our function given f prime of x equals, now the outer function is the sine hyperbolic inverse, so we start by using that derivative, which is the formula we have defined above, so that will be 1 over the square root of 1 plus, now here comes the composite form of it. The input for this function is negative 2x. So that's what goes in parentheses to be squared, such as the u squared in this kind of chain rule formula, right? So we have 1 over the square root of 1 plus u squared, where u is negative 2x in parentheses. But then we have to multiply by the derivative of u, that is u prime, in order to accomplish the chain rule. Well, thankfully, u is pretty simple here. This is just a negative 2x. The derivative of that, of course, is just negative 2. So that's all we want as the first step of accomplishing the derivative formula for this sine hyperbolic inverse. Of course, we want to simplify this a little bit, so we'll finish up that way. And so with one quick step to clean up that denominator, let's call it this. So f prime is going to be equal to negative 2 in our numerator. I'll just use that. The negative 2 that kind of popped out is that chain rule derivative. We're going to multiply that with the numerator of negative 1 just to put the negative 2 on top of it. You could put the negative sign even out in front of the fraction if you want instead of up with the 2. But ultimately you have a negative 2 factor in this numerator. And then down below we'll simply put the square root of 1 plus, now it's negative 2x in parentheses squared, which we know would simplify to be 4x squared. And so our final answer will simply be negative 2 over the square root of 1 plus 4x squared. And again, that negative sign, you might also see it simply written out in front of the fraction, or you could put it like we have here, up with the negative 2 in the numerator. Let's move on to another one. Our number 2 example is going to be this. Y equals cosine hyperbolic inverse of secant of theta. And we have a restriction where theta is greater than or equal to 0, but less than pi over 2. So like we just did in the previous example, I think it might be useful just to make sure we're clear on this, to write out the chain rule form for our formula above for cosine hyperbolic inverse derivatives. So let's do this. It's really going to be d over dx. So the derivative with respect to x, or actually in this case it's theta. So we'll say d over d theta. That's our independent variable here. I'm just putting the general chain rule form of this. So this would be cosh or cosine hyperbolic inverse of u, where again u is some function of theta. And this is going to be similar to the formula we have above, but with the chain rule involved. So this would be, if you look above, 1 over the square root of u squared minus 1, but then we have to multiply by the derivative of u, so we'll say times u prime. So again, this just uses the letter u, which is an implied function of theta in this case, theta being the independent variable provided in the problem. And this form of it helps us to remember and see, oh yeah, we have to multiply by u prime, the derivative of that inside function, to accomplish the chain rule here. If we now apply this chain rule formula for this derivative, it will be as follows. We'll say y prime equals, and then here we go, it's 1 over the square root of u squared minus 1. But now again, u is our inner function, which for this problem is secant of theta. So it's going to be secant squared theta minus 1 underneath our square root. So there's the first part of our derivative, 1 over the square root of secant squared minus 1. But then we have to multiply by u prime, that is the derivative of that inner function. The inner function here was secant, and so we just need to recall the derivative of secant is secant tangent. So we'll say secant theta tangent theta. And then there's some simplifying to do here. So let's carefully walk through some steps. You'll notice that down below our denominator of this fraction, we have the square root of secant squared theta minus 1. That may remind you of some trig identities we could use here. So let me just kind of recall this. I'm going to bring this in as some review of trigonometry, which may or may not be fresh in your mind. So let's recall that there is an identity where we could say secant squared theta equals 1 plus tangent squared theta. And the reason it's helpful to remember that is because what we have in our denominator underneath the root is a slightly different form of that. So notice what would happen if I subtracted 1 from both sides of this basic trig identity, that is the secant squared theta equals 1 plus tangent squared theta. If you subtract 1 from both sides, what we end up with is basically secant squared theta minus 1 equals tangent squared theta. Now, why does that matter? Well, because secant squared theta minus 1 is exactly what we have underneath our square root. So there's a bit of simplification we can do here that helps, well, it's helped by remembering that trig identity. So let's now go back to where we've been working and rewrite this with some replacements here. We're going to write this as 1 over the square root of, well, it's really just tangent squared theta. Again, that's what that identity was telling us. So we have 1 over the square root of tangent squared theta times secant theta tangent theta so far. And this is where we are. We're working on our derivative with the chain rule, which has already been accomplished. What we're trying to do now is simplify this. Now, notice in our denominator we have the square root of tangent squared theta. The question is, what is that, right? Do the square root and square just cancel out? Well, maybe. Let's recall very carefully with some algebra that the square root of x squared is the absolute value of x. And so we have to be a little bit careful with using the algebra here. If I use the simplification to rewrite this as 1 over, and I say, well, the square root of tangent squared theta is just tan theta, it's actually the absolute value of it. But this takes us back to the original restriction we had, which is that theta was originally given between 0 and pi over 2, that is greater than or equal to 0, but less than pi over 2. So if you think of where tangent is in that zone, which let me just kind of remind us here. We draw just a quick sketch for tangent of x or tangent of theta. I'll make it tan theta, a variable we're using here. In a very basic way, it's a graph that between 0 and pi over 2 is positive. So you can review what the graph of tangent looks like, but between 0 and pi over 2, which is where we're looking for this problem as given, in that little range, we're talking about a positive function, meaning it's all above the y-axis. Why does that matter? Well, because then the absolute value changes nothing. So since that's the case, we'll just call this 1 over Actually, let me not get ahead of myself. I'm going to keep by bringing down this secant theta, tangent theta, but now let's convert this by saying, well, the absolute value of tan theta, if theta is stuck between 0 and pi over 2, is the same as the positive. There's no difference with the absolute value. So we'll just call this 1 over tangent theta. Again, there's a little bit of algebra there. If you want to kind of rewatch or reach out with questions about that, that would be useful to make sure it's clear. So we have 1 over tangent times secant theta tangent theta. That is 1 over tan theta times secant theta tan theta. So all we want to do is simplify this a little bit further. And since algebraically now these tangents would simply cancel, our result is simply secant theta, which is exactly where we can finish. So there's a lot of moving pieces in this problem. It's not a bad idea to rewatch it to make sure that each step is clear. There's some hidden trigonometry recollection and algebra recollection with this whole absolute value thing. So make sure those steps are clear so that this result is believable and makes some sense. In fact, maybe it'd be helpful or fair for me to add a little bit more of a notation here. So why did the absolute value of tangent of theta turn into just tangent theta? Because with theta being between 0 and pi over 2, the absolute value of tangent theta equals tangent theta because the absolute value is that of a positive or quadrant 1 portion of this tangent function, which means the absolute value changes nothing. So that's why that's the case. All right, let's move on to a third example. This last one is given as y equals x times the sine hyperbolic inverse of x over 3, and then that is all minus the square root of 9 plus x squared. So there are really two larger terms to this function as provided. And we're also going to need to be careful to recognize that this first term is actually a product. This is x times sinh inverse of x over 3. So that is x times the sine hyperbolic inverse of x over 3. That's a product of two functions, x and the sine hyperbolic inverse of x over 3, which of course also involves a chain rule. So there's lots of pieces in this one. Let's see if we can keep it straight. That first term is going to need a product rule for derivative. We'll do that first. And then the second term is really just more of an algebraic, kind of older looking derivative, which we'll handle as well. So let's break this down here. We have y prime equals, here comes our derivative. For this first term, let's see, I have to color coordinate this so that it's a little bit better. But here comes the product rule. It's the first, which is the x, times the derivative of the second. Well, the second is this sine hyperbolic inverse of x over 3. This is going to use our formula from above, right? So if you look above and just kind of recopy what that is, the formula would be 1 over the square root of 1 plus the input squared. Now the input in this case is x over 3. Okay, so far we have x, that's the first, times the derivative of the second, which we're not even done with yet because we have 1 over the square root of 1 plus the input x over 3 squared. But then we have to multiply by the derivative of that inner piece. Here comes the chain rule, right? If you're using the u version that we wrote above, then we multiply by u prime. Well, if u is x over 3, then the derivative of that with respect to x is simply 1/3. So we'll have an extra 1/3 that's popping out from the chain rule there. But here we go. So that's first times derivative of the second. Continuing on, then we'll say plus the second, which is the sine hyperbolic inverse of x over 3. That's the second factor in our product function there. Second times the derivative of the first. Well, thankfully, the first being x has a derivative of 1, so that's going to be much simpler. All right, so that's really chain rule going on. Let's see if I can note that somehow clearly. So this first, I'll just give it a nice thick underline here. This first term in our function, which was x times sine hyperbolic inverse of x over 3. That turns into a product rule derivative, which we've now done. There's a lot of pieces involved there, but let's move on. So the second term now is just after the minus, and it's just a familiar algebraic term. This original function being being the square root of 9 plus x squared, that could be done. Recall that that's really just a power of 1/2. So if you take, let's see, I'm going to put this in here just to be extra clear. So this second term, let's recall that's really the same thing as 9 plus x squared in parentheses to the 1/2 power. That 1/2 power representing the square root there. So if we use it in that form, it's a little bit easier to do the derivative, which would be the power rule. So the 1/2 is going to come down in front. Right, and then we keep the inner function, 9 plus x squared, but then we decrease that power by 1, so 1/2 minus 1 would be now negative 1/2. And then we multiply, here we go, chain rule again, we multiply the derivative of the inner function, which was 9 plus x squared. Of course, the derivative of that would be then just 2x. Now, in order not to get lost in all the simplification that's about to happen, I'm going to color coordinate some things. If you look back at our previous step, right off the bat, in the first term, we ended up with an x and a 1/3 that were ultimately being multiplied together in this same first term. I'm simply going to summarize that as x over 3 that's out in the very front of what we have, just to keep something nice and concise there. And then I'm going to multiply it by what we have up there also, which is a fraction whose numerator is 1 and whose denominator is this square root. Now, inside the square root, we had 1 plus, and then it was x over 3 squared. I'm going to rewrite that as x squared over 9 instead of the x over 3 squared, because that's what it is. But then I'm also going to recognize that if you were to get a common denominator there, the 1 would actually be a 9 over 9. And then you'd have a common denominator which can be simplified further. So we'll hold on to that for a second and go further with it next. But that's kind of where that's all coming from. If we move on to our next term, it was just a sine hyperbolic inverse of x over 3 times 1. Thankfully, the 1 doesn't do anything for us, so we're just going to rewrite that as sine hyperbolic inverse of x over 3. And then, of course, moving on to our last term, which was just this algebraic term. Actually, some of it simplifies before we do anything else. We'll just kind of catch that now. So let's see. The 2 and the 1/2 would cancel just by fraction simplification. So we'll get that out of our way and simply call then this a fraction whose numerator is x from the single x factor we had at the end. But then this negative 1/2 power, this is going to throw a root in our denominator. So that'll be really x over the square root of 9 plus x squared that we had inside the parentheses that were all to that negative 1/2 power. All right, so we're just trying to clean up this algebra. I'm trying not to lose you along the way, show enough detail here, but also make some good progress to make this look a little bit better. If we take another step forward, let's see, we're just going to keep this x over 3 out in front where we can see it and use it. And that's being multiplied by our fraction, which I'm going to take another step on simplifying. So this will be now 1 over. We had the square root of, it was 9 over 9 plus x squared over 9, right? Well, that's kind of a mess. Let's call that this, the square root of, if I combine those fractions, it's really 9 plus x squared all over 9, just using a common denominator from those two previous fractions, right? And that's going to simplify for us even more. So I'm going to leave that alone for now, keep moving. So then plus sine hyperbolic inverse of x over 3, and then minus our last term, which we'll just leave as x over the square root of 9 plus x squared. Now let's work on this first term a little bit more. So notice that there's some simplifying we could do with this root of a fraction. If you take the square root of the top and the bottom, that is the denominator being 9, the square root of 9 actually will turn into a 3, which will cancel with the 3 that we have out in front of it. All right, let's take a couple more steps to simplify, but let's be very careful because out in front of what we have, which I'm going to mark as a caution for us, we have some dangerous fraction work going on. We're going to have to go very carefully through this first term to see exactly how it simplifies. And I'm drawing your attention to this because this is where a lot of mistakes happen. Quite honestly, a lot of little mistakes. It's not always the calculus that's the challenging part, it's the algebra. So let's be careful here. I'm going to continue on then with another step, and I'm going to try to write these levels very clearly. We have x over 3 as our first factor, and then we have a multiplication, fine. That's all I've put so far. And then next to it, we have another fraction. Now, in that fraction, the numerator is 1, but the denominator was a fraction also, which means it's actually a complex fraction. Well, let's be clear here. This means we have, if we split the root top and bottom, we have the square root of 9 plus x squared, and that's over the square root of 9, which is actually just 3. So that 3 is going to show up in the lowest denominator that we have. Now, how that simplified, we'll be very careful about that in a second here. But let's keep going. So we have plus sine hyperbolic inverse of x over 3 minus x. So we're just copying down the rest of this. Everything else is done here. Minus x over this square root of 9 plus x squared. Okay, so let's go back to that first fraction portion and carefully look at these. If I add in some extra dashed or dotted pink lines just to kind of keep things visually organized for us, let's keep track of these fraction levels. So I'm going to put a line directly across the largest fraction bar we have, which is of course the bar between the x and the 3 for x over 3. And then in our second factor, there's a 1 over this other fraction. Well, what divides the 1 from the fraction beneath it is a bar, but those are at the same level. So I'm going to put like a little dashed pink line through that. But then you'll notice we have another level of fractions going on. I'm going to put another dashed pink line to keep those straight. Here's why all this matters. Those 3's that we now have should actually cancel. Because notice they're on opposite levels and they match. So you could multiply by the reciprocal if you want to rewrite it even again. I don't think it's necessary to write that again. Let's recognize here that these 3's for the x over 3 and the 3 that's underneath now, the square root of 9 plus x squared, those 3's will cancel. Again, dividing by 3 is the same thing as multiplying by 1/3. If you kind of use that reciprocal trick and rewrite it even again, you'll notice that because those are on opposite levels and yet they match, they cancel. Now, why does that matter? Because that helps drastically simplify what we have. You'll notice then that this first term, which let me highlight here, or just kind of mark in a readable color. This entire first term now amounts to x over the square root of 9 plus x squared. Well, guess what? That's exactly what our last term is, except the last one is negative. So those completely cancel, which leaves us only with what we had in the middle, which is simply sine hyperbolic inverse of x over 3. Everything else cancels, which means that is our final result. Okay, there's a lot of detail there, a lot of simplification. If you want to go back through and rewatch just to make sure it's making sense, it's not a bad idea. In fact, I recommend that because you want to make sure these details make sense so that you could reproduce and try these on your own. Of course, work through the problems, work through the homework, make sure you can handle a problem like this in all of its detail.